Preventing lost updates. The read committed and snapshot isolation levels we've discussed so far have been primarily about the guarantees of what a read-only transaction can see in the presence of concurrent writes. We have mostly ignored the issue of two transactions writing concurrently. We have only discussed dirty writes. See no dirty writes on page 235. One particular type of write-write conflict that can occur. Roman 8. It is possible, albeit fairly complicated, to express the editing of a text document as a stream of atomic mutations. See automatic conflict resolution on page 174 for some pointers. There are several other interesting kinds of conflicts that can occur between concurrently writing transactions. The best known of these is the lost update problem, illustrated in figure 7-1 with the example of two concurrent counter increments. The lost update problem can occur if an application reads some value from the database, modifies it, and writes back the modified value. A read-modify-write cycle. If two transactions do this concurrently, one of the modifications can be lost, because the second write does not include the first modification. We sometimes say that the later write clobbers the earlier write. This pattern occurs in various different scenarios. Incrementing a counter or updating an account balance requires reading the current value, calculating the new value, and writing back the updated value. Making a local change to a complex value, for example adding an element to a list within a JSON document, requires parsing the document, making the change, and writing back the modified document. Two users editing a wiki page at the same time, where each user saves their changes by sending the entire page contents to the server, overwriting whatever is currently in the database. Because this is such a common problem, a variety of solutions have been developed. Many databases provide atomic update operations, which remove the need to implement read-modify-write cycles in application code. They are usually the best solution if your code can be expressed in terms of those operations. For example, the following instruction is concurrency safe in most relational databases. Similarly, document databases such as MongoDB provide atomic operations for making local modifications to a part of a JSON document, and Redis provides atomic operations for modifying data structures such as priority queues. Not all writes can easily be expressed in terms of atomic operations. For example, updates to a wiki page involve arbitrary text editing DDIA, but in situations where atomic operations can be used, they are usually the best choice. Atomic operations are usually implemented by taking an exclusive lock on the object when it is read, so that no other transaction can read it until the update has been applied. This technique is sometimes known as cursor stability. Another option is to simply force all atomic operations to be executed on a single thread. Unfortunately, object relational mapping frameworks make it easy to accidentally write code that performs unsafe read-modify-write cycles instead of using atomic operations provided by the database. That's not a problem if you know what you are doing, but it is potentially a source of subtle bugs that are difficult to find by testing. Explicit locking. Another option for preventing lost updates if the database's built-in atomic operations don't provide the necessary functionality is for the application to explicitly lock objects that are going to be updated. Then the application can perform a read-modify-write cycle, and if any other transaction tries to concurrently read the same object, it is forced to wait until the first read-modify-write cycle has completed. For example, consider a multiplayer game in which several players can move the same figure concurrently. In this case, an atomic operation may not be sufficient, because the application also needs to ensure that a player's move abides by the rules of the game, which involves some logic that you cannot sensibly implement as a database query. Instead, you may use a lock to prevent two players from concurrently moving the same piece, as illustrated in example 7-1. Example 7-1. Explicitly locking rows to prevent lost updates. The for update clause indicates that the database should take a lock on all rows returned by this query. This works, but to get it right, you need to carefully think about your application logic. It's easy to forget to add a necessary lock somewhere in the code, and thus introduce a race condition. Atomic operations and locks are ways of preventing lost updates by forcing the read-modify-write cycles to happen sequentially. An alternative is to allow them to execute in parallel and, if the transaction manager detects a lost update, abort the transaction and force it to retry its read-modify-write cycle. An advantage of this approach is that databases can perform this check efficiently in conjunction with snapshot isolation. Indeed, PostgreSQL's repeatable read, Oracle's serializable, and SQL Server's snapshot isolation levels automatically detect when a lost update has occurred and abort the offending transaction. However, MySQL/InnoDB's repeatable read does not detect lost updates. Some authors argue that a database must prevent lost updates in order to qualify as providing snapshot isolation, so MySQL does not provide snapshot isolation under this definition. Lost update detection is a great feature because it doesn't require application code to use any special database features. You may forget to use a lock or an atomic operation and thus introduce a bug, but lost update detection happens automatically and is thus less error-prone. In databases that don't provide transactions, you sometimes find an atomic compare and set operation previously mentioned in single object writes on page 230. The purpose of this operation is to avoid lost updates by allowing an update to happen only if the value has not changed since you last read it. If the current value does not match what you previously read, the update has no effect, and the read-modify-write cycle must be retried. For example, to prevent two users concurrently updating the same wiki page, you might try something like this, expecting the update to occur only if the content of the page hasn't changed since the user started editing it. If the content has changed and no longer matches old content, this update will have no effect, so you need to check whether the update took effect and retry if necessary. However, if the database allows the where clause to read from an old snapshot, this statement may not prevent lost updates, because the condition may be true even though another concurrent write is occurring. Check whether your database's compare and set operation is safe before relying on it. In replicated databases, see Chapter 5. Preventing lost updates takes on another dimension, since they have copies of the data on multiple nodes, and the data can potentially be modified concurrently on different nodes. Some additional steps need to be taken to prevent lost updates. Locks and compare and set operations assume that there is a single up-to-date copy of the data. However, databases with multi-leader or leaderless replication usually allow several writes to happen concurrently and replicate them asynchronously, so they cannot guarantee that there is a single up-to-date copy of the data. Thus, techniques based on locks or compare and set do not apply in this context. We will revisit this issue in more detail in linearizability on page 324. Instead, as discussed in detecting concurrent writes on page 184, a common approach in such replicated databases is to allow concurrent writes to create several conflicting versions of a value, also known as siblings, and to use application code or special data structures to resolve and merge these versions after the fact. Atomic operations can work well in a replicated context, especially if they are commutative, i.e. you can apply them in a different order on different replicas and still get the same result. For example, incrementing a counter or adding an element to a set are commutative operations. That is the idea behind RAIC 2.0 data types, which prevent lost updates across replicas. When a value is concurrently updated by different clients, RAIC automatically merges together the updates in such a way that no updates are lost. On the other hand, the last write wins LWW conflict resolution method is prone to lost updates, as discussed in last write wins discarding concurrent writes on page 186. Unfortunately, LWW is the default in many replicated databases. Write Skew and Phantoms. In the previous sections we saw dirty writes and lost updates, two kinds of race conditions that can occur when different transactions concurrently try to write to the same objects. In order to avoid data corruption, those race conditions need to be prevented either automatically by the database or by manual safeguards such as using locks or atomic write operations. However, that is not the end of the list of potential race conditions that can occur between concurrent writes. In this section we will see some subtler examples of conflicts. To begin, imagine this example. You are writing an application for doctors to manage their on-call shifts at a hospital. The hospital usually tries to have several doctors on call at any one time, but it absolutely must have at least one doctor on call. Doctors can give up their shifts, for example, if they are sick themselves, provided that at least one colleague remains on call in that shift. Now imagine that Alice and Bob are the two on-call doctors for a particular shift. Both are feeling unwell, so they both decide to request leave. Unfortunately, they happen to click the button to go off call at approximately the same time. What happens next is illustrated in Figure 7-8. Figure 7-8. Example of write skew causing an application bug. In each transaction, your application first checks that two or more doctors are currently on call. If yes, It assumes it's safe for one doctor to go off call. Since the database is using snapshot isolation, both checks return too, so both transactions proceed to the next stage. Alice updates her own record to take herself off call, and Bob updates his own record likewise. Both transactions commit, and now no doctor is on call. Your requirement of having at least one doctor on call has been violated. This anomaly is called write skew. It is neither a dirty write nor a lost update, because the two transactions are updating two different objects, Alice's and Bob's on-call records, respectively. It is less obvious that a conflict occurred here, but it's definitely a race condition. If the two transactions had run one after another, the second doctor would have been prevented from going off call. The anomalous behavior was only possible because the transactions ran concurrently. You can think of write skew as a generalization of the lost update problem. Write skew can occur if two transactions read the same objects, and then update some of those objects. Different transactions may update different objects. In the special case where different transactions update the same object, you get a dirty write or lost update anomaly depending on the timing. We saw that there are various different ways of preventing lost updates. With write skew, our options are more restricted. Atomic single object operations don't help, as multiple objects are involved. The automatic detection of lost updates that you find in some implementations of snapshot isolation unfortunately doesn't help either. Write skew is not automatically detected in PostgreSQL's repeatable read, MySQL/InnoDB's repeatable read, Oracle's serializable, or SQL Server snapshot isolation level. Automatically preventing write skew requires true serializable isolation. See serializability on page 251. Some databases allow you to configure constraints, which are then enforced by the database, for example uniqueness, foreign key constraints, or restrictions on a particular value. However, in order to specify that at least one doctor must be on call, you would need a constraint that involves multiple objects. Most databases do not have built-in support for such constraints, but you may be able to implement them with triggers or materialized views, depending on the database. If you can't use a serializable isolation level, the second best option in this case is probably to explicitly lock the rows that the transaction depends on. In the doctor's example, you could write something like the following. As before, for update tells the database to lock all rows returned by this query Roman 9. In PostgreSQL you can do this more elegantly using range types, but they are not widely supported in other databases.